This video introduces a real-world case study to demonstrate how DrainScope works and how effective it is. In this case study, we focus on the Bellinga drainage system in Odense, Denmark. DrainScope includes three views: a map view, an analysis view, and a comparison view. In the map view, we visualize the four components of a drainage system: catchments as polygons, junctions as circles, ditches as dashed lines, and conduits as solid lines. These components are color-coded based on their performance indicators. For instance, darker-colored junctions indicate a higher frequency of overflow. Overflow-prone junctions are one of the most critical system defects. Analyzing them is a key focus in DrainScope. To begin our analysis, we turn on region selection and draw a polygon to define the region of interest. Once confirmed, the system retrieves the most severe rainfall events that impacted the selected region. We choose one event of interest. The map view updates to show the system status during this event, and the comparison view shows the corresponding overflow condition. To understand the causes of overflow, we click on junction 303, the one with the most severe overflow. The Sankey diagram provides a visual representation of the water flow propagation associated with the chosen junction. The flow direction is from top to bottom and left to right. We use blue to indicate normal flow, pink to represent backflow, and gray to denote overflow loss. From this diagram, we observe that the inflow of 303 exceeds its outflow, resulting in overflow. The same pattern emerged in other events. Let's continue with event 139 as an example. We first try reducing the diameter of its upstream conduit from 0.191 meters to 0.14 meters to limit inflow. After simulation, a new bar chart appears in the comparison view, showing the overflow condition under this modification. This modification eases overflow at 303, but ends up causing worse overflow at the upstream junction, 304. So this modification is not ideal. Next, we increase the diameter of its downstream conduit from 0.18 meters to 0.26 meters to enhance outflow. This modification proves more effective. Overflow at 303 is significantly reduced without causing negative impacts elsewhere. However, severe overflow remains at junctions 011 and 307. Building on the second modification, we dig deeper. The Sankey diagrams reveal a similar issue at both junctions. Inflow exceeds outflow. To address this, we enlarge the diameter of their downstream conduits to 0.21 meters. We also enlarge the downstream conduits of nearby junctions by the same amount to maintain flow balance. After simulation, the overall drainage performance in this region improves substantially, with overflow frequencies significantly reduced. Before moving on, it's worth mentioning a small convenience feature. When we hover over a bar chart, the map highlights the modified components in red and shows tooltips with the details for each modification. Next, we look at another region that also has severe overflow issues. We select event 174, which exhibits the highest overflow in this region. Here, overflow-prone junctions are clustered in both the upstream and downstream segments. Starting with the upstream segment, we identify junction 454 as experiencing the most severe overflow. The Sankey diagram shows that its only downstream conduit experienced backflow. This backflow blocks the outflow from 454, eventually causing it to overflow. Tracing this backflow, we find that it originated from junction 450. The inflow of this junction exceeds its discharge capacity, causing water levels to rise, which in turn triggers backflow propagation to 454. A similar pattern is observed at junction 453. In the downstream segment, junction 430 shows the highest overflow severity. The diagram indicates that its inflow also exceeds its overflow, with the majority of this inflow originating from 450. We also see a similar pattern at other nearby downstream junctions. In sum, we identify 450 as the primary cause of overflow in this region. Interestingly, all the previous Sankey diagrams show that most of the inflow at 450 comes from catchment C1. We first reduced the impervious area percentage of C1 from 0.39 to 0.15 to reduce runoff generation. The resimulation results show a marked decrease in the overflow frequencies. But this level of impervious area is likely unrealistic given typical urban constraints. We also notice the adjacent region presents strong drainage performance, with only minimal overflow at its junctions. This suggests a promising improvement plan, rerouting flow from catchment C1 to junction 161 instead of 450. After running the simulation, we see a substantial reduction in overflow frequencies across all junctions here. And the adjacent region stays pretty much the same. These results confirm the effectiveness of the proposed improvement plan.